So thank you for joining me today, and I will present my PhD thesis about active perception for learning-based robot mapping, which I successfully defended in January this year. So let's first begin with the very fundamental question. Why do we need maps? In many scenarios, having a map of the environment is essential for many downstream tasks, not only for robotic applications such as path planning, localization, and interaction, but also for us humans to make informed decisions. You might ask, but why do we rely on mobile robots to create these maps? The reason is that mobile robots actually offer significant advantages when it comes to mapping. For example, in search and rescue missions, a robot dog can generate 3D maps of collapsed buildings, providing structural information to support rescue operations. And in industrial facilities, such as factories, oil rigs, or power plants, where human access can be difficult or even hazardous, an unmanned ground vehicle can map infrastructure for preventive maintenance and therefore reducing downtime and also improving worker safety. And most closely to our PhenoRob setup, in agricultural domains, a drone can efficiently map very large fields to monitor crop health or water distribution. This enables farmers to make data-driven decisions to improve productivity and also sustainability. However, when we think about robot mapping in an unknown environment, the image that often comes to our mind is a human operator manually controlling a mobile robot to build a map. But in many challenging scenarios, operating the mobile robots may require a certain level of expertise.
Stop!
And here is a video taken at the beginning of my PhD when my colleagues and I were attempting to map a cluttered orchard using a drone. And unfortunately, as you can see, a human operator like me can easily crush a drone into a tree, bringing the entire mapping campaign to a failure. This experience made me wonder, wouldn't it be great if we, as humans, only needed to press a start button and let the robot autonomously map the unknown environment for us? Yes, in some scenarios, this could be rather straightforward to implement. We can predefine a path or design simple heuristics for the robot to follow, and therefore eliminating the need for human operators during the online mapping mission. For example, following a lawnmower path pattern is a standard practice in many drone-based 2D field mapping applications. But what if we are more interested in specific parts of the field, such as areas with high width densities, like these two circles regions shown here? In this case, we would like to collect more detailed measurements or even perform closer inspection to map these regions, which might help farmers better deal with the weeds in the field. And now, following a rigid predefined path may no longer be effective, as it fails to account for the non-uniform distribution of the mapping targets. And since the spatial distribution of these targets is also unknown prior to data collection, we cannot design a path that densely covers these regions in advance. And all those things can get even more tricky when we now move from 2D to 3D unknown environments. In this case, predefining a path becomes extremely challenging due to the presence of unknown obstacles. So in both paradigms, the mobile robots cannot decide where to collect sensor data and to adapt its perception behaviors based on previously gathered information. This limitation introduces several downsides in traditional robot mapping systems. So human-aided mapping is labor-intensive and prone to human errors, while relying on predefined paths or simple heuristics can be inflexible and often limits its mapping performance across different environments. So in my PhD research, I aim to address this limitation by integrating active perception into robot mapping. And unlike traditional robot mapping systems, which treat the mobile robot purely as a passive sensor platform, active perception tightly couples mappings with view planning, and thereby closing the loop between perception and action. This enables the robot to autonomously decide where to collect data based on the current state of the map and to iteratively refine the map over time. For example, when mapping an unknown environment, the robot can detect unexplored areas and actively plan viewpoints in those regions to complete the map. Or the robot can identify low-quality areas in the build map, such as blurry surfaces on the right side, and perform targeted inspection to improve the map quality. In such active perception behavior, effective view planning always plays a central role. To carry out view planning, we typically require three components. First, an updated map represents the robot's current understanding of the environment. Second, a set of candidate viewpoints from which the robot can choose. And finally, a utility function to evaluate the expected usefulness of acquiring new measurement at each viewpoint. When formulating the view planning problem in a greedy manner, often referred as next best view planning in the literature, we can simply select the candidate viewpoint with the highest utility value as our next viewpoint. The main challenge, however, lies in designing a utility function that aligns well with the mapping objectives, while also accounting for the specific properties of different map representations. For example, most existing active perception methods rely on voxel map, which divides the space into regular grid cells labeled as unknown, free, or occupied. In this setting, the mapping objective is often full coverage of the scene, and the utility is typically defined by how much unknown space can be observed from a viewpoint. And similarly, for other conventional map representations such as point clouds or meshes, the utility formulation also needs to be tailored. However, all of these representations are built on rigid geometric primitives that require spatial discretization. This can often limit the fidelity of the resulting maps. And in contrast, throughout my PhD research, I have focused specifically on learning-based map representations, maps that can be iteratively optimized given online sensor data or modeled with learning-based techniques, such as neural networks. And compared to conventional map representations, learning-based methods can often capture fine-grained details and represent scene in a continuous manner, and therefore achieving better mapping quality. Building on this foundation, I have proposed active perception method using 4 such representations, including Gaussian processes, image-based neural rendering, semantic neural resonance field, and Gaussian splatting. However, due to time constraint, today's talk will be based on 2 of those proposed works. And we first start with active perception for robot mapping using image-based neural rendering. So image-based neural rendering is a mapping technique that, given a set of reference images as input, a pre-trained neural rendering network can render the RGB and arbitrary normal viewpoints to represent the scene. In order to gain this rendering capability, we need to first train this neural rendering network on multi-view dataset offline. So how does this work under the hood? Let's consider how we render an image from normal viewpoint. We first encode the nearby reference image into a feature map W using an image encoder. For each ray cast from the normal viewpoint, we densely sample points along the ray, and each sampled point is then projected onto the reference image plane to retrieve the corresponding feature from the feature map. The 3D position of the sample, the view direction of the ray, and the retrieved feature vector are then fed into the rendering network, which predicts the RGB color and density at the sampled point. And by repeating this process for all sampled points, we can obtain a discretized distribution of colors and densities along the ray. We then use volume rendering, a formulation that integrates all these individual predictions to yield the final rendered color of the ray. Now, the difference between this rendered color and the ground truth color provides the training signal, which we use to update the network weights. So in this paradigm, once the neural rendering network has been trained, we only need to collect reference images to provide this information. These reference images, together with this pre-trained neural rendering network, then serve as a map representation of a specific scene. For example, given reference images of different scenes, the same network is able to represent each scene in a continuous manner. However, you may also notice that in each of these scenes, from some perspectives, the rendering results appear more blurry than from others, which means the mapping quality is not spatially consistent. Why does this happen? This is because the choice of reference images really matters for rendering performance. For example, when we now rendering the same normal view using 2 different sets of reference images, you can clearly see the performance gap. The first reference image set contains sufficient scene information to support the rendering of the novel viewpoint, while in the second case, the reference images are far from the novel viewpoint, making it difficult for the rendering network to render accurately. In our active perception setup, our goal is to actively collect new reference images from informative viewpoints in order to improve rendering quality across the entire scene. This naturally raises the question, how do we determine which viewpoint is more promising to visit? In other words, how do we define the utility of a viewpoint? One straightforward idea would be identify viewpoints where the rendering performance is poor, such as those with high rendering error. Because as mentioned in the previous slides, poor rendering performance often indicates a lack of scene information around these areas. However, this idea is infeasible for online mission, because we do not have ground truths to evaluate the rendering performance at novel viewpoints. And therefore, we need another method to estimate rendering performance without relying on ground truths. To address this issue, we propose a novel uncertainty-aware image-based new rendering network. Previous work typically output single RGB values, providing a point estimation. And under this formulation, the network cannot expose its confidence about the prediction. In any cases, the network will give you some RGB values without telling you how reliable these predictions are. We instead want to know how confident our network is about its rendering at a certain viewpoint, when given a set of reference images. To this end, we model the RGB prediction in logit space and assume its logits follow normal distribution, with mean and variance predicted by our network. This gives us two benefits. First, we can ensure the resulting RGB values are always valid between 0 and 1 after passing the logit through a sigmoid function. And second, and more importantly, we can now use a variance to quantify the uncertainty of network predictions. Specifically, we encourage the network to output high variance when its RGB predictions are unreliable, and low variance when it can produce accurate renderings. And the secret to achieving this lies in the uncertainty-aware loss function used for training our network. Here, Y, the ground truth color, and mu sigma are the color mean and variance predicted by our network. The subscript I indicates different color channel. And the loss can be decomposed into reconstruction loss and regularization loss. As you can see, the reconstruction loss can be decreased either by predicting accurate mean value closer to the logit of ground truth value or by predicting high variance values. However, only relying on this term cannot lead to meaningful distribution learning, since the network can always output high variance in all cases to reduce the loss and fool the training. So we need this second term, which we call regularization loss, to penalize unnecessary high variance predictions. Under this formulation, the network finally learns to predict accurate mean and low variance when the reference images are informative enough to condition the network's rendering at the novel viewpoint, but only high variance when the reference images cannot support accurate mean prediction. Now, given reference images, our novel network not only predicts the color, but also the associated uncertainty at any novel viewpoints. And you can see that when the network renders blurry RGB results, it also outputs high uncertainty in the corresponding areas. And this is a desirable property that we want. We demonstrate that our uncertainty estimates closely align with the true error map. This shows that our uncertainty is well calibrated and serves as informative proxy for this unavailable rendering error. So if we get high uncertainty rendering from a viewpoint, highly likely our network will also perform poorly at this viewpoint as well. And this insight gives us now a powerful tool. We can now render at any novel viewpoints and identify viewpoints where our network is less certain about the rendering output. And we leverage this uncertainty rendering as a utility of a viewpoint and guide our view planning to collect more reference images around these uncertain viewpoints. And here we show the framework of our approach. So given currently collected images from the scene, we use them as reference images to render uncertainty map at sampled viewpoints. We then select the viewpoint with the highest average uncertainty as our next best viewpoint and move the camera there to capture a new image. We add this new image into our image collection to expand our understanding of the scene. And we repeat this process until we exhaust the mission budget, such as maximum number of images to be collected. And here we show an example of the reference images collected by different planning methods, along with the corresponding rendering results. We report PSNR as a rendering quality metric, which describes the pixel-wise similarity between two images. And a higher value indicates better rendering quality in our case. And since the same network is used for rendering evaluation, any performance difference arises solely from the choice of reference images. And we compare with heuristic-based approach by selecting the viewpoint that maximizes the distance to all previously visited viewpoints and also compare to random selection. The reference images selected by our uncertainty-guided approach significantly improve the rendering quality around the scene, achieving better overall mapping performance. And we further visualize the visited viewpoint distribution in another example. As you can see, our approach allocates the viewpoints in a targeted way, with denser inspection around more complex regions, where the network struggles to render accurately. And in contrast, heuristic-based approach or random sampling cannot adaptively plan the viewpoints based on the target to be mapped. The effectiveness of our view planning strategy is further validated by overall higher random performance using the reference images collected at viewpoints planned by our approach. So to summarize this part, we introduce a novel uncertainty estimation method in image-based new rendering network, which we utilize to guide our view planning to actively select reference images. And we show that these informative reference images collected by our approach indeed improve overall random quality. However, this mapping technique is not without limitations. To render each pixel, or namely for each ray, image-based new rendering relies on dense sampling to retrieve this information, and each sample requires a network inference. For example, rendering a single image at a resolution of 100 by 100 pixels with only 10 samples per ray already result in 100,000 network queries. Although we can process these queries in batches, the computation is still expensive and poses challenges for runtime efficiency. This naturally motivates the second part of the talk, which I move on to another more efficient map representation called Gaussian splatting, a recent mapping technique that has gained enormous interest in the robotics community due to its highly efficient rendering pipeline. A Gaussian splatting map consists of many 3D shape primitives called Gaussian splats, each defined by its optimizable attributes in color, opacity, scale, rotation, and position. You can imagine these splats as ellipsoids with their opacity fading outward according to Gaussian distributions. This is also why they are called as Gaussian splats. Suppose we now have several images of a scene and want to train a Gaussian splatting map to represent the scene. For each of this training image, we project Gaussian splats onto the image plane. We then order the Gaussian splats based on their distance to the image plane and blend or overlap Gaussian splats to get final rendering results. Notably, this rendering process can be done within 5 milliseconds, making it highly efficient. We then compare the rendered image with ground truth images to compute rendering loss. And because the rendering process is differentiable, this loss can be backpropagated to update the attribute of all involved Gaussian splats. And by iteratively updating the Gaussian splats under the supervision of multiple images, the Gaussian splatting map can gradually generate better rendering results. Here we show an online training process of Gaussian splats. As you can see, in the beginning, the Gaussian splats generate blurry rendering results, and over time, as they are updated, the rendering becomes much more photorealistic. However, integrating active perception into Gaussian splatting-based mapping systems faces two main challenges. First, Gaussian splats often show varying rendering quality across different viewpoints, as they can easily be overfit to training viewpoints but cannot generalize well to unobserved viewpoints. To enhance this overall mapping performance, we need to evaluate the quality of a Gaussian splat and capture more images around low-quality areas to better constrain the Gaussian splatting training. And second, since Gaussian splats only model the same surfaces, we cannot distinguish between free and unknown space with Gaussian splatting map alone. However, this spatial information is very important for robot operating in the 3D unknown environment. So to address the first challenge, we introduced confidence modeling of Gaussian splats, which allows us to identify under-reconstructed areas in a Gaussian splatting map. Inspired by multi-view stereo approaches, we assign high confidence scores to Gaussian splats that are densely observed from diverse viewpoints, as they are better constrained during online training and often yields better random results. In contrast, we give low confidence scores to Gaussian splats that are sparsely observed from similar viewpoints, as they often fail to generalize to novel viewpoints. And by explicitly modeling the confidence of each Gaussian splat, we can use the same random pipeline to render per pixel confidence at any novel viewpoint. We show two examples of RGB rendering and their corresponding confidence rendering from the same viewpoint, but obtained under different training conditions. The example on the left is trained with dense training image taken from diverse viewpoints and therefore show sharp, high-quality RGB rendering with high confidence. And in contrast, the example of the right is trained with sparse training images and produce blurry RGB rendering with overall low confidence. This indicates that our confidence rendering is informative to identify the low-quality surfaces in the Gaussian splatting map, which we leverage to guide our view planning. And to address the second challenge, we combine Gaussian splatting with a cross-voxel grid to create a hybrid map, which we use a Gaussian splatting for high-fidelity mapping and cross-voxel grid for spatial occupancy modeling. The voxel map encodes information such as unexplored or free space, which we utilize to guide our robot exploration and enables collision-free path planning. In the view planning step, the utility of each candidate viewpoint is evaluated based on the confidence rendering from the Gaussian splatting map and the number of visible unexplored voxels in the grid. This allows our approach to balance between targeted inspection around areas with low confidence Gaussian splats and exploring previously unseen areas. Now, putting everything together, we present the framework of our approach. Given the current hybrid map, we first identify unexplored regions in the voxel map, as well as areas with low confidence Gaussian splats in the Gaussian splatting map. We then generate candidate viewpoints around these regions and select one with the highest utility value as the next target viewpoint. Next, we plan a collision-free path to reach its next best viewpoint, which the robot follows to collect new measurements. And this new measurement is used to update the voxel map, spawn new Gaussian splats in previously unseen areas, and of course, together with our previously measurements, to continuously train the Gaussian splatting map online. We now show an example of our active mapping process in the simulator. On the left, we show the rendered RGB of the current Gaussian splatting map with planned camera viewpoint shown as green pyramids. And in the middle, we show the surface normal rendering, which reflects scene geometry quality. On the right is a confidence rendering, where reddish areas highlights low confidence Gaussian splats. And our approach actively targets these areas to improve the Gaussian splatting map quality. Let's now take a look at the final mapping result from our online mission. We show RGB rendering and a mesh extracted from the Gaussian splatting map. As you can see, our map captures photorealistic scene details, such as light on the wall and texture on the furniture, while also preserving pretty accurate scene geometry. And for quantitative evaluation, we plot the mapping performance over mission time. We report color rendering quality in PSNR and mesh quality in completeness ratio. Our approach outperforms other state-of-the-art baselines, achieving better rendering quality and more complete coverage in a limited mission time. And beyond a single scenario, we further test our approach across different scenes to assess its generalization to mapping 3D unknown environments. Our approach effectively balances exploration of unknown areas with detailed inspection of low-confidence surfaces, ensuring both efficient coverage and high-quality mapping. And as a result, our approach shows the best performance in both metrics across all testings, demonstrating its robustness in different environments. And now let's get back to the question I posed at the beginning of this talk. Can we now let a robot autonomously map an unknown environment, and more importantly, can do so while producing a high-fidelity map? With the method I just introduced, the answer is yes. We can simply press the sub button and let the robot do the job for us. So here's a video record of a real-world experiment using our approach, where we use an unmanned ground vehicle equipped with a RealSense RGBD camera to actively reconstruct the kitchen in our lab. The robot conducts the mapping mission in a fully autonomous manner without any human intervention. And on the top right, you can see the incrementally generated Gaussian splatting map outline. And we now show the final Gaussian splatting map obtained from the mission. Overlaid on the map, the green triangles indicates the viewpoint planned by our approach, where the robot collects measurement to train a Gaussian splatting map, while the red triangles denotes normal viewpoints that the robot has never visited before. As you can see, our Gaussian splatting can render detailed images at normal viewpoints to review the scene structure and appearance. And to conclude this part, we proposed one of the first active perception method for Gaussian splatting-based mapping. We introduced a simple but effective confidence modeling technique to evaluate the quality of Gaussian splats. We use a hybrid map representation that utilizes Gaussian splatting for high-fidelity mapping and voxel map to guide exploration and assist in path planning. Combining these two contributions, our approach achieves strong performance in both rendering quality and map completeness in mapping unknown environments. And with this, I come to the end of my talk. So in today's talk, I introduced active perception for robot mapping and discussed why it is valuable for autonomous robotic systems. I presented two methods for active perception using learning-based map representations, where the key is specifically designed utility formulation, such as uncertainty estimation in image-based new rendering and confidence modeling of Gaussian splats. Due to time constraints, I was not able to cover all of my work, but you are very welcome to export my thesis for additional details. So taken together, these results from my PhD thesis demonstrate that by coupling learning-based map representations with effective view planning techniques, we now enable fully autonomous robot mapping systems that is capable of producing high-fidelity scene representations.